Hello! What I've got for you today is a video on circular motion, and this is a mathematically very simple problem, but conceptually it gets into a lot of good stuff. So this is a good one to start watching if you're still figuring out, okay, how does this circular motion stuff work? So the problem we have is, during a Halloween party, you are spinning a toy around in a circle. And the toy is a skeleton head on a bone. So I really can't draw a skeleton head. There's our skeleton head. And then it's on a bone. How do you draw a bone? There. And you're grabbing it. And you're spinning it in a vertical circle at a constant speed. So we're spinning it in a vertical circle at a constant speed. Okay, so a constant speed. That's the good thing for circular motion. We need a constant speed. And remember that constant speed does not mean constant velocity. Constant speed means your speedometer is going the same thing. Constant velocity means your speedometer and your direction are the same thing. We're changing direction, so it's not constant velocity, just constant speed. When the skeleton head is at the 3 o'clock position, the stick tension is 16 newtons. Find the tension in the bone, stick tension. The bone tension is 16 newtons. Find the tension in the bone when the ball is at the 12 o'clock and 6 o'clock positions. So when our little skeleton head is at straight up and straight down, we want to know what the tension is. Okay, so what are our knowns? There's our picture. Great picture. And we're going to spin this in a vertical circle. When the skeleton head is at the 3 o'clock position, the stick tension is 16 newtons. So at the 3 o'clock position, the tension is 16 newtons. So at 12 o'clock and 6 o'clock, what is the tension? And we're given the mass, oops, forgot that, 0.020 kilograms, 20 grams, very light. So not a lot of tension. Well, yeah, 16 newtons, not a lot of tension. All right, so with our problem solving, we have the picture, we have our knowns, we have our unknown, and typically what we do next for a forces problem is pick the object of interest and do the force diagram. The object of interest here is going to be the skeleton head, the ball at the end. That's the thing we have the mass of, and that's the thing that is moving in the circle. So I'm going to start by drawing the force diagram of it when it is at the 3 o'clock position. So when it's here. So there's our 3 o'clock position. So when it's moving in a vertical circle and it's at the 3 o'clock position, what forces are acting on it? So 3 o'clock position. All right, here's our little skeleton head. We always have our weight acting straight down. And then we're ignoring the force of air resistance. The only other thing interacting with the skeleton head is the bone that it's on, our little stick. So what direction is that bone or stick pulling or pushing on our skeleton head? Well, when we're at this position, it's got to be tugging it in to keep it going in a circle. That's the direction that it's connected in. So we're going to have the tension in that bone or stick going this way at the 3 o'clock position. All right, so we have that. What else? Forces are friction? No, it's not touching any other surfaces. So really, this is it. That's how easy the force diagram looks like at the 3 o'clock position. Now, one of the things we want to make sure we do with circular motion is with each force diagram, at that moment, we want to figure out what direction the acceleration is. So we have a vertical circle. And for circular motion, the centripetal acceleration, the circular acceleration, always points to the center of the circle. So at every point here, the acceleration is always pointing towards the center of the circle. Which means, for this thing right here, our acceleration is pointing to the left, and it is centripetal. It's a centripetal acceleration to the left. All right. So that's what we've got. And now after the force diagram, you can do your XY chart. So in the x direction, if I do my standard coordinate system, we have 0 and negative mg our weight goes down, and then I've got a negative tension, and that's nothing in the y direction. How exciting, right? And in the x direction, that's the direction with an acceleration, so that's unbalanced. Y direction, we have balanced forces. So once we get to this point, I think, okay, well, what are we looking for? We are asked to find the tension at this point and this point in the circle. So straight up and straight down in the circle. Okay, so the tension's going to change. If you've ever swung something in a circle, you know it's heavy at one point and light at another point. What do we need to know in order to get the tension? Okay, let's do that. So let's just start with the 12 o'clock one. So for the 12 o'clock position, it's right there as I've drawn it. So what forces act on our skeleton head ball? We've got our weight acting straight down, and our tension is going down. And at this point, at the top of the circle, the acceleration is also pointing straight down. So here, our XY chart is nothing and nothing and nothing there. We have a negative mg, we have a negative tension, and that's it. And we don't have any X forces, the Y forces are, unbalanced. Oops, bad me. Unbalanced, because that's the direction of the acceleration. We get so used to doing balanced forces in the Y. Unbalanced. So if we want to know what the tension is, let's figure out what that is. Okay, so it's unbalanced, which means the net force in the Y direction has to add up to equal ma in the Y direction. Add up all the forces. We have a negative mg, we have a negative tension, equals our mass times the acceleration in the Y direction. And now here, the acceleration is centripetal acceleration. It's also going down. I'm going to include that negative there. If I solve this, oh man, for tension, bring that over. So I should get an equation of MAC minus mg for the tension. I know the mass, I know the acceleration due to gravity, I need to know the centripetal acceleration in order to get the tension. So how can I get the centripetal acceleration? Well, they gave us the tension at 3 o'clock in this problem, so I'm guessing that's going to be helpful. So let's see if we can figure something out for the 3 o'clock situation where we were given a bunch of information. So if we do the X and the Y for the 3 o'clock position, X is net force equals ma because that's unbalanced. So I have a minus t equals ma. And that's centripetal. Oh, and look at that. My centripetal acceleration is going to the left. I need to sneak in a negative sign there. There we go. Okay, and you can do the y direction equation, but I'm probably not going to need it. If you want to do it, net force. Ooh, did I say it was balanced in the Y direction? I was wrong. Hopefully you caught me. It's unbalanced in both directions. There's no way to balance up down if there's only one force. So in the Y direction, also unbalanced. So here we'd have negative mg equals ma y. All right, that's not very exciting. This is the centripetal acceleration. So can I use this information to figure out what the centripetal acceleration is? Well, sure. I know what the tension is at this point. I know the mass. So that's why I'm saying this one is mathematically a little bit easier. So my acceleration in the centripetal acceleration is tension divided by mass. That gives me a huge number, 800 meters per second squared. Wow. Okay, now that is the centripetal acceleration at the 3 o'clock point. Is that constant all the way around the circle? Well, we know we have a constant speed, and we're assuming we have a constant radius. If you're moving it in a circle means a constant radius. So our definition for centripetal acceleration is v squared over r. If the velocity is the same, gotta be careful, the speed is the same, and the radius is the same, all the way through the circle, the centripetal acceleration is the same all the way through the circle. So this is the centripetal acceleration any point in that vertical circle. So now I know that. I can solve for my tension right here. So the tension at 12 o'clock is 0.02 times 800 minus 0.02 times 9.8. Ooh, squeezing it in. And if you do that calculation, you get, what do you get? 15.8. 15.8 at 12 o'clock. Right around 16. Okay. Is that reasonable? Yeah. If we were at 16 newtons here, then being at 15.8 up here, it's in the right ballpark, so I'm going to guess that is a reasonable number. Now we wanted the tension at 6 o'clock as well. So we need to do the same thing. And I'm going to erase my 3 o'clock because we have all that data that we need. So while I'm erasing, you think about what the force diagram looks like at 6 o'clock when the bone and the skeleton head are straight down. So what forces act and what directions are those forces? And once you get that, then can you figure out what direction the centripetal acceleration is? So think about that while I'm erasing, and hopefully you will beat me to it. Oh, come on. It's always so hard to erase. Okay. So what do we have here for 12 o'clock that we had? So now it's 6 o'clock. So we're down here. The forces acting are, well, we always have our mg straight down. And the bone, again, is pulling up in this case. That's the direction that it's attached. So we have tension up, mg down, and at the bottom of the circle, the centripetal acceleration points towards the center of the circle, which is like that. And I'll get rid of this so I don't confuse you. Alright, so we've got that for our force diagram. If you do our little XY chart, again, there's nothing in the X. And we have a positive T, a negative mg. So the net force in the Y direction, unbalanced, equals MAY. Add up all the forces. Plus T minus mg equals MA. So my acceleration vertically is my centripetal acceleration, and it is positive. It's going up in this case. Solve this for the tension. mg plus ma. So this is 0.02 times 9.8 plus 0.02 times 800. And if you do that math, you should end up with a tension of 16.2 newtons. So again, ask yourself, is it reasonable? Well, we had 16 newtons at 3 o'clock. We had 15.8 at 12 o'clock. If we have 16.2 down here, that seems very reasonable. So the numbers seem reasonable. Does the size of the number make sense? If you've swung something in a circle, if you think about where it was hard to swing, it's hardest to swing at the bottom and it's easy to swing at the top. Because at the bottom, you're having to exert a lot more tension on whatever it is you're swinging. So I would expect that there would be the most tension at the bottom, at the 6 o'clock position, the least tension at the top, at the 12 o'clock position, and then, of course, it's about halfway in between at 3 o'clock. And now you should be able to just say, okay, I already know what the tension is at 9 o'clock. You got it? You got it? It should be 16 newtons. It should be exactly the same as the 3 o'clock position. So that was mathematically easy. Really not too hard for the math, but conceptually it's good because we had to think about what the force diagram looked like at all these different positions, and also what direction the centripetal acceleration was in all those different positions. So we've got the answer, we've answered the question, which is the tensions, and they're reasonable, and it makes sense in terms of which is biggest, which is smallest, so I think we've got it. Good job.